unprecedented pictures of a newly discovered exoplanet. So what's an exoplanet, you ask? That is a planet that is outside our solar system. And this is the first time that telescope has discovered a new planet.
We're tracking something unprecedented in Earth's skies. 3I/ATLAS, a Manhattan-sized interstellar object initially classified as a comet, just did something comets aren't supposed to do. It lost its tail. When astronomers first spotted this visitor from beyond our solar system, everything seemed normal. Like other interstellar travelers, Oumuamua and 2I/Borisov, it appeared to be a typical icy wanderer ejected from a distant planetary system drifting through the cosmic void between stars. But then the tail vanished. Completely. This wasn't gradual sublimation or normal comet behavior. The characteristic streaming trail of gas and dust that defines comets simply disappeared from observations, leaving scientists scrambling for explanations. Comets lose their tails when they move away from the sun's heat, but 3I/ATLAS was getting closer, warming up. Its tail should have been growing brighter, not vanishing. The implications hit the astronomical community like a shockwave. If it's not behaving like a comet, what is it? Some researchers began whispering what others considered unthinkable. This might not be a natural object at all. Could we be looking at something artificial? An alien craft? The speculation ignited global interest, but scientists needed data, not theories. That's when the James Webb Space Telescope entered the picture. If any instrument could pierce through the mystery and reveal what 3I/ATLAS truly was, it would be Webb's unprecedented infrared capabilities. What Webb discovered would reshape our understanding of interstellar space forever. This wasn't just a comet misbehaving. The tail loss was merely the first clue in a puzzle that would reveal something far more extraordinary than anyone anticipated. As Webb's instruments locked onto the target and began capturing detailed spectra and images, astronomers prepared for answers. Instead, they got questions that challenged everything we thought we knew about how planetary systems evolve and what travels between the stars. When the James Webb Space Telescope turned its infrared eye toward 3I/ATLAS, astronomers expected to see a modest interstellar visitor, similar to previous detections. What they got instead was a revelation that would rewrite the textbooks. Webb's near-infrared camera, NIRCAM, began its deep imaging campaign as the object entered a region where both ground-based telescopes and space observatories could track it clearly. Initial optical data had suggested a dim, slow-moving body, likely just a few kilometers across. Nothing extraordinary, just another piece of cosmic debris wandering between stars. But infrared doesn't lie. As Webb's instruments collected light across multiple wavelengths, that faint speck transformed before scientists' eyes into something far more complex. The intensity and wavelength distribution of the thermal emission revealed a rich tapestry of reflected sunlight and heat radiation that simply didn't match the previous estimates. The infrared brightness was stunning. When astronomers compared it to predicted reflectivity values, the numbers didn't add up. The surface area required to produce that much thermal emission was orders of magnitude larger than anyone had calculated. This wasn't a small rock tumbling through space. This was something immense. Webb's sensitivity allowed researchers to capture details invisible to conventional telescopes. The infrared spectrum showed subtle variations across the object's surface, warmer regions, cooler zones, and a distribution of thermal energy that painted a picture of shocking scale and complexity. Previous observations had categorized 3I/ATLAS as unremarkable, but Webb revealed the truth hiding in the infrared spectrum. The thermal profile indicated a body with significant mass and surface area, something that challenged fundamental assumptions about what could be ejected from a planetary system and survive the journey through interstellar space. The imaging data kept getting stranger. Instead of a uniform brightness, Webb detected patterns, variations in how different regions emitted heat. This suggested a heterogeneous surface with varying compositions, not the simple icy body everyone expected. Within hours of the first deep images, the astronomical community knew they were dealing with something unprecedented. Webb had turned routine observation into one of the decade's most significant discoveries. The calculations came back, and scientists couldn't believe what they were seeing. 3I/ATLAS wasn't a few kilometers wide, it was hundreds of kilometers across. This revelation sent shockwaves through the astrophysical community. To put this in perspective, this interstellar object wasn't asteroid-sized or even large comet-sized, it was dwarf planet scale. a body comparable to some of the substantial moons orbiting gas giants in our own solar system, except this one was traveling between stars. Webb's infrared measurements provided the definitive proof. By analyzing the thermal emission patterns and comparing them to the amount of sunlight the object reflected, astronomers could calculate its true dimensions with unprecedented accuracy. Every analysis pointed to the same staggering conclusion. 3 I/ATLAS measured hundreds of kilometers in diameter. This scale completely overturned our models of interstellar objects. Small comets and asteroids can be ejected from planetary systems relatively easily. Gravitational interactions with gas giants, the chaotic dynamics of young star systems, or resonant orbital patterns can fling smaller bodies into the interstellar void without extraordinary circumstances. But something this massive? That requires extreme events. Objects of this magnitude aren't casually tossed out of planetary systems. They're gravitationally significant with enough mass to resist perturbation. To eject 3 I/ATLAS from its home system would require energies and gravitational interactions far beyond what previous models had considered possible for creating interstellar wanderers. Scientists immediately began proposing catastrophic origin scenarios. Perhaps 3 I/ATLAS was the fragmented remnant of a dwarf planet torn apart by extreme tidal forces near its parent star. Maybe it was a piece of a disrupted moon, shattered during a massive impact or gravitational encounter. Some speculated it could be a planetesimal core, the dense building block of planets, expelled before it could accrete into a full world. Whatever its origin, one thing was certain. The universe had just shown us that interstellar space harbors giants, and we'd barely begun to understand their implications. The size of 3 I/ATLAS forced scientists to confront an uncomfortable truth. They were looking at a planetary corpse. This wasn't debris from a comet or fragments of a shattered asteroid. This was a piece of a world that once was. The evidence pointed toward a violent origin story. To create an object this massive and then fling it into interstellar space required gravitational forces beyond ordinary planetary system evolution. Traditional models suggested large bodies remain gravitationally bound to their stars, while only smaller objects get scattered into the cosmic void. 3 I/ATLAS broke those rules completely. Researchers developed several catastrophic scenarios. The leading hypothesis suggested that 3 I/ATLAS originated as part of a differentiated body, a moon or dwarf planet that had undergone geological evolution, developing distinct layers of core, mantle, and crust. Something massive happened to this world. Perhaps it orbited too close to its parent star and was torn apart by tidal forces, the same gravitational stress that creates Saturn's rings from shattered moons. Another scenario involved a close encounter between stellar systems. In dense stellar nurseries where stars form in clusters, gravitational interactions are common and violent. Two star systems passing within a few light years could gravitationally strip planets and moons from each other, sending massive fragments on escape trajectories into interstellar space. The most dramatic possibility involved a stellar flyby so close it destabilized an entire planetary system. Imagine a rogue star passing through the outer regions of a solar system, its gravity yanking planets from their orbits, smashing moons together, and scattering the wreckage across light years. 3 I/ATLAS could be one survivor of such cosmic carnage. What makes this hypothesis compelling is the object's structural integrity. Despite whatever violence ejected it, 3 I/ATLAS remained intact through millions, possibly billions, of years traveling through interstellar space. It survived cosmic radiation, micrometeor bombardment, and the absolute cold of the void. This wasn't random rubble. This was a cohesive fragment of a world, carrying within its frozen layers the memory of catastrophe and the chemical fingerprint of an alien planetary system long since transformed or destroyed. Webb's spectroscopy capabilities revealed that 3 I/ATLAS wasn't just large, it was chemically bizarre. The mid-infrared instrument, MIRI, detected a molecular cocktail that defied expectations and hinted at formation conditions radically different from our solar system. The spectral signatures showed a complex mixture: ices, silicates, metallic compounds, and organic molecules embedded within the frozen crust. At first glance, this resembled comets from our own solar system. But the ratios were all wrong. Methane, carbon dioxide, and exotic hydrocarbons appeared in unexpected proportions. The chemical fingerprint suggested formation in an environment with higher radiation levels or different elemental abundances than exist near our sun. This wasn't just alien material, it was material forged under alien conditions. MIRI detected subtle absorption bands corresponding to ammonia hydrates and carbon-rich compounds. These molecules pointed toward a world that had experienced thermal processing, possibly from internal heating due to radioactive decay or tidal stresses from a nearby massive planet. The presence of these compounds meant 3I/ATLAS had a geological history, a past where internal heat drove chemical reactions and transformed its composition. Even more intriguing were the organic molecules. Webb identified polycyclic aromatic hydrocarbons and nitriles, complex carbon molecules known as precursors to amino acids. These are the building blocks that, under the right conditions, can form the basis of prebiotic chemistry and eventually life itself. The discovery reignited debates about panspermia, the hypothesis that life's ingredients, or even life itself, could travel between star systems on objects like 3I/ATLAS, while the extreme radiation environment would make survival of actual organisms nearly impossible. The presence of complex organics proved that the chemical seeds of biology could absolutely be distributed throughout the galaxy. Every large interstellar fragment drifting through space might carry the potential ingredients for life, waiting to be delivered to a young planet where conditions allow those molecules to evolve into something extraordinary. 3I/ATLAS wasn't just a rock, it was a cosmic seed bank, carrying alien chemistry across the gulf between stars. Webb's continuous monitoring revealed something else unusual about 3I/ATLAS. It rotates incredibly slowly. Most asteroids and comets spin rapidly, completing rotations in hours. 3I/ATLAS takes several days to complete a single turn. This sluggish rotation, combined with its massive scale, told scientists something crucial about its internal structure. The object wasn't a loose collection of rubble held together by weak, cohesive forces. It was a monolithic fragment, bound together by its own significant gravitational field. The data was unmistakable. When scientists analyzed how sunlight and Webb's infrared beams scattered off the surface, they could calculate the object's mass and density. The results indicated a body with substantial gravitational cohesion, internal gravity, strong enough to hold hundreds of kilometers of rock, ice, and metal together through millions of years of interstellar travel. This changed everything about how we understand interstellar objects. Many asteroids in our own solar system are rubble piles, collections of fragments loosely bound together, easily disrupted by close encounters or impact events. 3I/ATLAS was fundamentally different. Its structural integrity suggested a cohesive, differentiated body with a dense core and layered composition. The slow rotation also provided clues about its violent past. Rapidly spinning objects typically form from collisions or fragmentation events that impart angular momentum. Slow rotators suggest different origins, perhaps tidal locking to a former companion, or simply that the catastrophic event that ejected it didn't impart significant spin. Webb's instruments detected subtle wobbles in the rotation pattern, indicating an asymmetric mass distribution. The object wasn't perfectly uniform. Dense regions in its core pulled slightly differently than lighter ice-rich areas near the surface, creating minor variations in how it tumbled through space. This complexity reinforced the picture of 3I/ATLAS as a genuine planetary fragment, something that had undergone differentiation, where gravity and heat separated materials by density, creating the layered structure we see in planets and large moons. The gravitational analysis proved that interstellar space doesn't just contain small debris. It harbors genuine world fragments, massive cohesive bodies that once belonged to planetary systems and now drift eternally between the stars. The most tantalizing discovery came when astronomers modeled 3I/ATLAS's internal composition. The density calculations, derived from its size and the subtle effects of solar radiation on its trajectory, suggested a mixed structure, a dense, rocky core overlaid by thick layers of ice and dust. This configuration was startlingly familiar. It echoed the structure of ocean moons like Europa, Enceladus, and Ganymede, worlds with subsurface oceans beneath frozen crusts. Could 3I/ATLAS once have harbored liquid water? Webb's spectroscopy provided compelling evidence. Certain spectral bands corresponded to minerals that only form in the presence of liquid water or at high temperatures. These minerals, hydrated silicates, and specific crystalline structures, require water in its liquid phase to develop. Their presence on 3I/ATLAS meant that at some point in its history, before ejection into interstellar space, this object likely had liquid water in contact with rock. The implications were staggering. If 3I/ATLAS once had subsurface oceans, it might have possessed the conditions necessary for prebiotic chemistry, or even primitive life hydrothermal vents, organic molecules, liquid water, and energy from tidal heating or radioactive decay, all the ingredients life needs. Scientists found additional evidence in the thermal processing signatures. The crystalline ice detected by Webb forms at relatively high temperatures and persists as long as it remains undisturbed. Its presence indicated that 3I/ATLAS had experienced warmth, perhaps from internal heat generated by tidal forces when it still orbited within its original planetary system. The possibility that this interstellar wanderer carried within it the frozen remnants of an ancient ocean, and potentially the chemical traces of alien biochemistry, transformed it from an astronomical curiosity into one of the most profound discoveries in astrobiology. Interstellar space might be filled with fragments of ocean worlds, each one a time capsule preserving the conditions and chemistry of environments where life could have emerged. These cosmic messengers drift silently through the galaxy, occasionally passing through new star systems where they might seed young planets with complex organic molecules and the essential chemistry of life. The discovery of 3I/ATLAS fundamentally changed how we view interstellar space. What we once thought of as empty void is actually a graveyard and library combined, filled with the wandering remnants of dead worlds, each carrying the chemical fingerprints of alien planetary systems. Researchers began calling these massive fragments rogue relics. They're remnants of destroyed planets, shattered moons, and failed worlds that never completed their geological evolution. But far from being cosmic garbage, these objects serve a crucial role in galactic evolution. When a massive fragment like 3I/ATLAS passes through a young star system's protoplanetary disk, it doesn't just pass by harmlessly. It can seed that nascent system with exotic materials, heavy elements, complex organic molecules, and unusual isotopic ratios that wouldn't naturally exist in that region of the galaxy. Essentially, interstellar visitors act as galactic gardeners, distributing chemical diversity across light years. This has profound implications for how planets form and evolve. Every solar system might be influenced by interstellar contributions, material from other stars, other planetary systems, even other regions of the galaxy with different chemical compositions. The elements in Earth's crust, the organic molecules in our oceans, might include contributions from interstellar visitors that passed through our solar system billions of years ago. The case for panspermia grew stronger with 3I/ATLAS. The complex organic molecules detected on its surface, polycyclic aromatic hydrocarbons, nitriles, and carbon chains, are known precursors to biological chemistry. If objects this size routinely travel between stars, carrying these molecules, then the galaxy isn't a collection of isolated chemical environments. It's an interconnected network where the building blocks of life circulate continuously. Webb's discovery suggested that if we could detect one massive interstellar fragment, countless others must exist. Most pass through the darkness unnoticed, too distant or too dim to see. Only when they enter the inner solar system and reflect sunlight do we spot them briefly before they vanish back into the void. The galaxy suddenly seemed less empty, more alive with wandering worlds, silent witnesses to ancient catastrophes, carriers of alien chemistry, potential messengers between civilizations separated by time and space. Webb's high-resolution infrared imaging revealed 3I/ATLAS's surface in unprecedented detail, and what astronomers found was a geological wonderland frozen in time. The terrain showed a strange dichotomy, smooth, reflective regions interspersed with darker, pitted areas that absorbed more light. The contrast suggested a violent geological history. The smooth areas might represent ancient resurfacing events, perhaps cryovolcanic eruptions that flooded portions of the surface with fresh ice. The darker, cratered regions bore the scars of impact, collisions that occurred when 3I/ATLAS still orbited its parent star, possibly within a chaotic ring system or debris field. Webb detected bright flashes of reflected infrared light as the object slowly rotated. These corresponded to ice cliffs, steep, reflective surfaces glinting as they caught sunlight at specific angles. These formations suggested massive fractures running across the surface, cracks that might have formed during the catastrophic event that ejected the object, or from thermal stress as it alternately heated and cooled over millions of years. The infrared mapping revealed deep basins and towering ridges, creating a three-dimensional picture of alien topography. Some craters appeared partially filled, hinting at past geological activity that had modified the surface. After initial formation, fissures ran for hundreds of kilometers, geological scars preserved in the near absolute zero temperatures of interstellar space. Most intriguing were the thermal hotspots. Webb's thermal mapping showed localized regions warmer than the surrounding crust. These weren't dramatically hot, nothing like volcanic activity, but measurably warmer than they should be given the ambient temperature of deep space. Scientists proposed several explanations. The hotspots might indicate pockets of trapped internal heat, remnants of the thermal energy the object possessed when it was ejected. Alternatively, slow chemical reactions could be occurring beneath the ice, exothermic processes that release small amounts of heat over geological timescales. The presence of these warm zones suggested that 3I/ATLAS isn't entirely geologically dead. Even after eons drifting through the cosmic void, internal processes continue, energy reservoirs persist. The object remains, in some limited sense, active, a frozen world that still carries faint echoes of its dynamic past. The discovery of 3I/ATLAS marks a turning point in how humanity approaches space exploration. We're no longer limited to studying distant exoplanets through indirect methods. Interstellar visitors bring samples of alien worlds directly to our cosmic doorstep. Mission planners immediately recognized the opportunity. Proposals emerged for high-speed interception probes capable of reaching interstellar objects during their brief passage through the inner solar system. A spacecraft equipped with sampling instruments could collect actual material from another star system: dust, ice, perhaps even fragments knocked loose by controlled impacts. This would be the ultimate sample return mission: alien planetary material analyzed in Earth laboratories. 3I/ATLAS, despite being beyond practical reach for current technology, serves as proof of concept. Its immense size and relatively slow speed make it an ideal target for future mission planning. Engineers now have concrete data, trajectory, composition, rotation rate, to design intercept scenarios for the next interstellar visitor. The discovery also emphasized the critical need for next-generation observatories. Webb demonstrated what infrared sensitivity can achieve, but we need more wide-field surveys capable of detecting these objects earlier in their approach. Would provide more time for study and potential interception. Ground-based telescopes equipped with adaptive optics and space-based observatories working in concert could map an entire population of interstellar wanderers. Beyond the technical implications, 3I/ATLAS carries profound philosophical weight. It proves that planetary systems are not closed loops. Matter, chemistry, and potentially even the precursors of life circulate throughout the galaxy on cosmic timescales. The boundaries between star systems are porous. We're all connected through this slow exchange of material across light years. Every piece of 3I/ATLAS's frozen crust is older than our solar system, carrying within it the chemical memory of an alien world that may have existed and died before Earth formed. It's a humbling reminder of the deep time scales of cosmic evolution and the impermanence of worlds. The galaxy isn't empty space punctuated by isolated solar systems. It's a living, interconnected web where worlds are born, destroyed, and scattered, their remnants drifting eternally between stars. Silent witnesses to billions of years of cosmic history, waiting for instruments like Webb to read their stories.